Advances in Ray Tracing. Today I will introduce what Ray Tracing improved in RE engine after the GDC Resident Evil Village talk. I will break it down into 3 parts. First, I will go over denoiser improvements and try to give you inspiration on how I think when dealing with problems. Next, I will share the new features in Ray Tracing that were added in latest RE engine. Finally, I will give you Ray Tracing and the denoiser's GPU execution time in PS5 as a reference. At GDC in 2021, the presentation, Resident Evil Village, our approach to game design, art direction, and graphics, was given. Please reference these for details. To recap, DirectX 12 PS5 acceleration structure API was implemented, and Ray Tracing members introduced the way to optimize BVH building times, especially for skeletal meshes. We also implemented geometry to texture mapping framework in RE engine. As for performance concerns, RE engine uses JSON file to map textures instead of supporting user shaders for ray tracing. As for me, after a basic ray tracing framework is established, the potential performance for consoles is checked and limited for ray tracing. With a low sample rate, the final results are full of devastating noise. I tried to solve this noise in the meantime, optimizing ray tracing and shading cost. At that time, no official denoiser framework was provided. I researched and invented some of the methods, like indirect dispatch for wavelet filter, which saves more than half of the cost of denoiser. And the step for history is adjusted. View-independent history calculation could be calculated at first for dynamic tracing dispatch. Some of these technologies I learned from other companies and improved them. For example, I tried several guided filters, wavelet and bilateral. The most important thing for the filter is consistency. At the same time, it should be as close as the ground truth result as possible. Please see GDC 2021 for more details. Improvements start from this problem. Artists want to use lights freely. Lights like emissive and image-based lights are highly dependent on the surrounding geometry environment. Some light can be difficult to sample because rays don't know where the light is if we don't tell them. The problem we need to solve is creating all the passes between the light source and the camera. For example, we trace a diffuse ray for 64 samples. Only one of them hit the light, so 63 miss the target and get black result. If we can only trace one sample per frame, you will see 63 black frames with one lighted frame. That causes high variance and noise. What expected is 64 frames with the same result as one frame lighted result divided by 64. Buffered light, like directional, punctional, area light, relieve this problem. The light buffer is looped and the lights are connected to hit geometry, which causes the next event estimation. You just need to check the visibility turn to ensure that the light can be reached. But geometry light, such as emissive and image-based light, is difficult to sample. We don't know where the light is. If the ray didn't hit the light, we cannot create the light path, which makes this situation need far more rays compared to buffered light environments. Still, I want to solve this problem with limited samples, or at least improve it a little. So, the image you see on the left of the slide is the shading result from image-based light with shutter. I only traced the first bounce. Most of traced rays cannot reach the light, which causes sparse results here. 500,000 rays are traced. Only thousands of pixels hit the light. We got the shading result, depth, and the normal buffer for guiding filter. What makes it more difficult is I need to make the result convergence and consistent from one-frame tracing. If I cannot denoise it through one-frame data, when I move the camera, you will see artifacts from some of the disocclusion pixels. And here is the comparison between previous result and what improved now. Here is the video comparison. You can see noise is substantially reduced with this approach, while detail is preserved. So, how do we reach this result? There are several ways through which we can reach a good result. If you try and dig it deeper, all roads lead to Rome. I will summarize what I tried to solve these problems. Machine learning is the best fit for denoiser. UNet is widely used in biomedical image segmentation and image upscaling. Recently, Transformer also integrated to the UNet framework. The intuitive idea for UNet is to compress the source data to multiple feature levels and learning from the most abstract level. For reconstructing, all these level features are used to improve final quality. Separating source data into multiple features is critical for denoising. Actually, it's also important in most computer vision machine learning algorithms. The reason it's not selected is because current generation consoles cannot afford the cost. I do research through PC with different machine learning framework. Although I don't have enough time and budget to implement machine learning framework in RE engine. But if you do, using machine learning for the denoiser could result in the best quality. The same decompression idea is basically used to denoise even multiplayer perceptron is not used. The Delaunay triangulation method. Sparse diffuse ray samples are similar to the left image from the paper. A Voronoi diagram can be generated from point clouds. If the surface is a plane, we can expect that the lighted pixel distribution is correlated to its surrounding luminance. Why is the diffuse result to a low frequency output? Because it propagates the light uniformly. Without geometry interference, the propagation from samples should be consistent even with a limited sample rate. Sparse point cloud distribution should be the same as an aggregated samples distribution except the high frequency geometry aliasing. The same idea is used in irradiance catching with V-ray. You can see Delaunay triangles are generated and the result for the luminance is interpolated through each vertex and divided by the triangle's area sides. The difficulty is creating precise Delaunay triangles that cling to 3D geometry. Even with guided buffers, 2D Delaunay triangles will sometimes give disfigured results. A 3D Delaunay algorithm could cost more in performance for real time. But solving geometry consistency is the critical issue for this method. I would like to call it Lagrange method, because it uses discrete points to reconstruct the result. Another thing is the generation, and the propagation steps are not very fast with this method. I didn't spend too much time on optimizing it, but if you put your energy into optimization, it could work better. The probe approach is one widely used in Unreal Engine and is called Lumen. The difficulty is also in the interpolation. However, they improved this method to the extreme. Performance and quality are balanced. Actually, the probe approach needs pretty tricky adjustments and several guided buffers are used. As far as I know, Epic Games uses Spent Normal SSAO to improve the quality. Just read their code, you will find all the answers. They have done a considerable amount. In my opinion, it won't be easy to go beyond what they have already accomplished. Guiding redirection to the light also seems feasible. Compared to cosine hemisphere distribution, guided direction gets more lighted result. This method can be implemented using reservoir sampling. Actually, the most important parameter through Monte Carlo method is PDF. Reservoirs save all possible directions for the light and its PDF. The tricky thing is you cannot always use accumulated data. Instead, you need to update and clean reservoirs to refresh your image. The time when you clean is dependent on your implementation. For example, wrong accumulated data could be destroyed through moment buffer. Correct history data could be regularly updated, jittered by pixels. For the implementation, I separate two redirection buffers into guided and default. Then, I bind them randomly if the history is enough. The guiding direction and its PDF are updated from reservoir sampling. Guided history can accumulate up to 500 frames. The result is pretty good if accumulated history is used. The disadvantage for this method is noise cannot be solved from one-frame data. Actually, we do the same thing with spatial and temporal accumulation using the moving average weight, which is even more aggressive for the samples. Only if the reservoir buffer accumulates enough history will the guided direction be acceptable and the PDF precision be enough to use. You cannot guide the direction if you don't have history. So, as previously mentioned, we try to solve noise only using one-frame data. That doesn't help for this purpose. How about guiding light position from the camera distance field? If emissive, image-based light's position is saved to buffers like punctual light, you just need to do what the next event estimation did to connect the path and the short visibility rays. If the hit geometry is emissive, it's simple. You can get the position from the geometry. If IBL is hit, you need to take the nearest distance to that focal point. So, rematching through camera distance field is possible if the camera distance is larger than the rematched distance, which means you are inside the room. If the camera distance is smaller than rematched distance, this means you are outside the room. After getting those light positions, propagate them to those pixels without light and do the next event estimation at the final stage. The reason why I didn't use this method is because it needs shadow rays to check if small geometry lights are reachable. Geometry lights don't have shadow maps. Another reason is because the camera distance field is needed and there's not enough budget. Still, depending on the concrete problem you need to solve, this method could give you precise, accelerated result from one-frame data. The objective for this method is to try to build an automatic polygon light system through traced lighted geometries. If the development is in the early stage, polygon light could also be set by the artist. Another idea is tracing more rays, depending on the history. Artists don't want to make visual changes to their product close to the game's release. They only want to denoiser works better in difficult scenes. And the console performance is not acceptable for tracing too many rays. In some difficult scenes, results cannot be convergent even if tracing 128 rays per pixel. You need to propagate low-frequency light while preserving high-frequency visibility. So, extract useful information, reducing the buffer size and make it enough to propagate. The same idea is used across all other research, such as machine learning. The buffer is squeezed to a small resolution, while consoles use checkerboard, which is much smaller. In this buffer, 16 to 64 rays is traced per pixel. Comparing the results of 540-piece image with 1 sample per pixel and the 67-piece image with 64 samples per pixel, 67-piece image is substantially clear and easier to propagate. And a good reconstruction algorithm is needed after that. Reconstruction blends the guided color buffer and the moment buffer to generate an upscaled result. The guided buffer is responsible for the light field changes, while the moment buffer is responsible for geometry changes. So, why does this work? The result can be separated into light contribution and visibility term. Light contribution for GI is propagated diffusely and continuously. After propagation, only low-frequency output remain, which means it can be compressed in low dimension. On the other hand, visibility term is high-frequency geometry information, and it is critical to the final image quality. Two steps have been used to reconstruct the visibility term. The moment buffer is used to block the light from rough geometry, and a more precise normal map is used to sketch the details for geometry occlusion. Now, let's talk about how to propagate through low resolution and how to reconstruct it back. It's actually similar to a multi-grade linear solving method. If the high-frequency geometry term is separated at first, the result could be better for reconstruction. Wrong interpolation will lead to aliasing and get a numerical error. As the result, for details, please see the related papers. So, to not make the logic too complicated, even the result contains some numerical error or aliasing from inadequate smooth decomposition, there is a way to relieve the problem, jittering. And another jitter is executed after blending the image from temporal accumulation. Another problem that was pointed out by the artist is when light changes quickly from auto-exposure. Incorrect result is caused by filtering in nonlinear space. The reason is because the Reinhardt curve compressed the color. It is not correct to filter from results that use the Reinhardt curve. Another reason is temporal luminance-based rejection was not used before, because it will increase the noise clamping from one frame-only buffer. First, I will show you the comparison between previous and current results. Instead of using Reinhardt curves, aggressive denoiser logic and other deflaker logic are added to remove valve lights. Compared to the previous method, it's not easy to remove linear color noise. Additional steps are added, but we will touch on this later. After the Reinhardt curve is removed, the brightness is totally changed, and the emissive brightness issue that artists tend to complain about is solved. In previous version, the light was set by a high intensity value. Due to the effect of the Reinhardt curve, the result will not be as bright as you thought. With that removed, the light balance, which was adjusted by the artists, is broken. So, this feature can only be used for new titles. The linear result is more difficult to denoise, especially for high-intensity lights. Light is propagated linearly, which means more steps are needed. 3 more guided propagation passes are added to relieve this problem. The visual quality is upgraded compared to previous. The contrast of the image is increased, and the light is more balanced. Besides removing the Reinhardt curve from the framework, the temporal luminance rejection is also improved. Luminance rejection solves dynamic light switching problems. The stabilized one-frame result is used to recertify the history. Other methods, like light buffer flags, can also be used to relieve history light ghosting problem, which caused by luminance changes. Fake specular is used when the roughness exceeds the threshold, for example, 0.3 before, which causes material incoherence and incorrect results. A reason to use fake specular is because specular rough ray could be as expensive as diffuse ray. In most conditions, rough specular can be denoised using the same policy as diffuse denoiser. The difference is that rough specular BRDF is a view-dependent lobe. Accumulating spatial reusable results needed more precise calculation. Depending on title's budget, high-resolution and low-resolution traced specular buffers are separated. Different scale filters are used with different approaches. I don't have enough time to focus on rough specular denoiser, but it could be improved in the future. Specular ghosting is not resolved from the previous temporal motion. The main reason is that some of the wrong motion is not removed correctly. If viewed closely, the image is broken up. But if you aren't close and the camera movement isn't that fast, the result is also acceptable from the previous result. However, this is my mistake and I improved it. Now let's compare results between the previous and the current. Thin lens motion is used before improving the motion from curved geometry. For performance issues, planar virtual position is totally enough for most cases. Moment clamp is used for the motion of animations in mirrors. Specular clamp is different to diffuse. Instead of using history, color clamp is also needed to maintain visual quality. The final result is merged based on moment buffer. For shading, rendering unit members implement user-shared related support. Complicated shading models are also in development. Light visibility tests could be cached to a hash table. It's meaningless to test all the lights for every frame. It could be done in the future. Many new features have also been added to RE engine from the rendering unit members. Mirror transparency is handled especially with separate implementation. Only perfect reflection is supported, and no denoiser is used for performance consideration. Effect ray tracing is also implemented by the effect unit members. In most cases, the same denoiser progress is shared after shading. Rectangle, disk, line light are also implemented by another rendering unit member. Both direct and indirect area light shadows are supported. Terrain and speed tree ray tracing are also supported by rendering unit members who are responsible for landscapes and foliage. BVH's data doesn't completely match G-buffer's position, so ray offset or additional rays are needed to avoid the self-intersection. As for title use cases, 3 versions of shading and denoiser system are created to keep raised title stable. Version 1 is only used in Devil May Cry 5 Special Edition. Version 2 is more widely used in titles like Resident Evil Village, Resident Evil 7, Resident Evil 2, 3, 4 remakes, and the Exo Primal. Resident Evil 4 only uses ray tracing reflection for performance issues. And version 3 is the one showcased in today's presentation, which will be used in future titles. This data was taken from GDC 2021's performance cost on PS5. You can see that ray tracing in total cost 4.7 milliseconds. Tracing and shading cost 2.3 milliseconds. Others like generated ray direction and sorting cost 0.2 milliseconds. Denoiser cost 2.2 milliseconds. Compared to the previous version denoiser, spatial propagation steps were added, which is about 1 millisecond. On the other hand, wavelet filter logic is removed, and additional disocclusion rays are traced, which is about 25% of the total tracing and shading cost. So the new method is more rays dealing with noise. Additional costs depend on how tracing and shading cost through the scene. As for denoiser, disocclusion rays help stabilize denoiser, and the wavelet filtering is no longer needed in the final step. However, for dealing with rays from disocclusion and upscaling, additional spatial steps are added, leading to a total of 0.5 millisecond cost. In conclusion, those are the various ways in which ray tracing was improved in RE Engine. The presentation mainly focused on GI denoiser-related improvements due to the fact that it is a difficult topic and valuable to share and discuss. Specular-related improvements were also introduced. Many people contributed to the new features for ray tracing, but I was only able to briefly mention some of their work due to time constraints. I also touched on PS5 performance costs, comparing the previous denoiser to the current one. That concludes this presentation. Thank you for your listening.